Welcome! In this video, I'll show you how to solve problem 2.45 as it appears in the third edition of Griffiths Introduction to Quantum Mechanics. Now, this problem states the following. It says, show that this wave function satisfies the time-dependent Schrödinger equation for the harmonic oscillator potential. Here, A is any real constant with the dimensions of length, and part B asks us to find the probability density for this function and describe the motion of the wave packet. And C asks us to compute the expectation value for the position and momentum and check the Ehrenfest theorem, or check that the Ehrenfest theorem is satisfied. So this is not really that much of a terrible problem. The expression is of course nasty, but what we have to do is not really difficult. So in part A, we want to see that this satisfies the time-dependent Schrödinger equation. Now, what is that? The time-dependent Schrödinger equation is minus h bar squared over 2m, second derivative of our wave function with respect to x, plus the potential, which in this case is 1/2 m omega squared x squared. And this has to be equal to, and now let's not only write the energy, but actually the operator of the energy, which we haven't used in a while, but it's IH bar d dt psi. So this is the equation that the wave function has to satisfy. So we need to calculate this part here, basically the derivatives with respect to time and with respect to space. We can start with any of them. I'm going to start with the spatial derivatives. So that is our wave function. Now, if we derive with respect to x, there's only an x here and here. So, and this, of course, all inside an exponent, right? The e to the this power. So we have the constants m omega pi h bar to the 1/4. And then we get the exponent again, right? Because since we are deriving the exponent, we get the exponent times the derivative of what is inside of the exponential. So for that reason, we get the same exponential here, but this entire thing is simply our wave function once again. So we get our wave function psi times what is in here. So what is the derivative of what is inside? We get minus m omega divided by 2h bar. And then derivative of x squared is 2x. There's no x here, no x here. Then we have minus 2a e to the minus I omega t. Okay, so this is the first derivative. Now we want to derive that. So second derivative. Now this is the derivative of psi with respect to x times this parentheses. But this derivative is precisely the parentheses. So we get that parentheses squared. So we get, this minus will be a plus. I'm going to write it like this. So m omega 2h bar, and all of this is squared. And then we get this thing here. So 2x minus 2a e to the minus I omega t squared times psi. And of course, now we need a second term because of the product rule. So now we need to derive this part. So we get plus, and the only thing with an x is this. So we get minus m omega times 2, but there's a divided by 2 here, so we can write it as minus m omega divided by h bar times psi. Now what we could do as well is see that there's a 2 here and a 2 here. When we take them out, if we factor them out, it's going to be a 4. So we can cancel them out with this 4 down here. So this and this and this are now gone. So there we go. This is the second derivative. Now let's go for the time derivative. So the time derivative of that thing, so I'm going to do it in green, so d psi dt. Now, looking at this expression, and this is going to be the same as before, right? We will have first psi, because we have the constants here, and then the exponent, which will not change. And then we multiply by the derivative of what is inside of the exponential. And let's see, what here has a t? So we'll have to derive this part, and this part. So those are the three terms. So deriving of what is inside, we have this m omega divided by 2h bar, which is factoring out or multiplying everything. And then we have a squared over 2 times the derivative of this. So we get minus 2i omega times the exponent, so minus 2i omega t. And then we have this part, which is plus I h bar over m. And finally, we have this part. So we get minus, but when we derive for this, another minus. So we get plus I omega 2ax e to the minus I omega t. And we close parentheses. All right. Now, there's a few things to simplify. So this 2 and this 2. And yeah, I think that's it. But let's try to simplify this expression before we continue. So by multiplying through, we get psi times, and now let's see. In this first term, we get a squared, the minus cancel out, m omega squared divided by 2h bar. And let's see, we still need to include the I, e to the minus 2i omega t. Let me double check. So a squared, m omega squared, I positive 2h bar, yes. Now we multiply this part, so we get minus I, the h bar cancel out, the m cancels out, omega divided by 2, double check again, there, minus I omega 2. And then finally we get minus, and now the 2's cancel out, so we get I omega squared m, the 2 cancels out, a x, and divided by h bar. iw to a, let's see, the 2 cancel out, a x w squared, I, the minus sign, the m, the 2 cancel, the h bar, okay, and e to the minus I omega t. There we go. And what is I h bar d psi dt? Well, we simply have to multiply this by I h bar. So we get I squared, so we get a minus sign, a squared m omega squared e to the minus 2i omega t divided by 2, the h bar is gone, now plus omega h bar over 2, and here we get plus an m omega squared a x e to the minus I omega t. Okay, and we can also just, to make everything a bit smoother, we can calculate minus h bar squared over 2m, because this is what we will have to calculate, to plug into the Schrödinger equation. So this is what we have up here times minus h bar squared over 2m. So this is minus h bar squared over 2m times m omega divided by h bar squared times, and I'm actually going to multiply through, so I'm going to expand that square, so x squared minus 2ax e to the minus I omega t plus a squared e to the minus 2i omega t squared. Actually, no, squared, I already squared it. Okay, and then we have the second term, which is minus h bar squared over 2m times minus m omega over h bar. And all of this is, of course, multiplied by psi. Okay, so let's see. Here we can simplify the h bar squareds. We get m omega squared divided by 2. And then we have everything else. So x squared minus 2ax e to the minus I omega t, blah, blah, blah. And then we have plus h bar omega over 2. Okay, and we can now multiply through this part. So we get m omega squared x squared over 2. Oh, where's the minus sign? I almost forgot to multiply through. Basically, that minus sign should be right here. There we go. So when we multiply, we get minus this plus the 2's cancel out, m omega squared ax e to the minus I omega t, and then minus m omega squared a squared over 2 e to the minus 2I omega t. And yeah, and then we have this other part. So h bar omega over 2. Okay, so now what we need to do is plug everything into the Schrödinger equation, which is this part right here. I think I'm actually going to reuse this because we need to plug in this part, which we just wrote, plus the potential times psi, of course. I forgot to write it before, but of course it's times psi, and then equal to IH bar, which we times the time derivative, which is right here. So we got this plus 1/2 m omega squared x squared psi, and this has to be equal to what we have in green up there, which is minus a squared m omega squared e to the minus 2I omega t divided by 2 plus h bar omega over 2 plus m omega squared ax e to the minus I omega t times psi, of course. Now notice that we have this on one side, this on the other. They cancel each other out. We have m omega squared ax e to the minus I omega t. This cancels out this. Then we have minus a squared m omega squared blah blah blah, which is exactly the same as this, except that it's in a different order. Here we have m first. And we have this, which cancels out with the potential. So we have 0 equal to 0, right? This is indeed true. So we just showed that this wave function does indeed satisfy the time-dependent Schrödinger equation for the harmonic oscillator potential. Now we wish to find the probability density. So to do that, we need to take this wave function. I think I'm going to steal it. I'm going to move it to the side so that we can write in peace. And what we need to do is do psi squared, right? Which means psi conjugate psi. So that means that our constants here, this will be squared. So that will be m omega pi h bar times the square root. And then we have this thing. So we will have exponent, I'm just going to write it like this, of. And now m omega divided by 2h bar factor of. Now this part, the x squared, is real. So we are going to add the same thing. So the x squared will not change. So we have x squared times 2. Then we have this part, which is also real. So we get twice that. So we get a squared, right? And I broke up the parentheses here. Then we have this, which is not real. So here we get a squared over 2 e to the minus 2I omega t. But then we get plus a squared over 2 e to the 2I omega t. Right? Then we get plus I h bar t over m minus I h bar t over m. And finally, we get minus 2ax. Here I'm going to factor this out. E to the minus I omega t plus e to the I omega t. So there we go. That is what we get. And now there's a few things that we can simplify. So this and this cancel out. And notice what we have here. So there we can factor out a squared over 2. So we can factor out a squared over 2, and we get 1. And we get e to the 2i omega t plus e to the minus 2i omega t. Now this should ring a bell, as should this part right here, because this is 2 times the cosine of 2 omega t. And this part right here is 2 times the cosine of omega t. Okay, you need to know that I'm going to write it here, that the cosine of x can be written as e to the ix plus e to the minus ix over 2. That is incredibly important, right? That's going to come up constantly during your physics courses, so you need to learn that. Okay, so this is 2 cosine of 2 omega t, and then we have this, which is 2 times the cosine of omega t. Now we made some progress, but this isn't really all that pretty just yet. So we get the exponent of minus m omega over 2h bar, 2x squared. And now these 2's cancel out. Oops. So notice we have a squared here and here. So we could factor out a squared, and we get 1 plus cosine of 2 omega t minus 4 times ax cosine of omega t. And now this we can simplify further. So these constants here will remain the same, the exponent of. And now let's look at this for a moment. Let's pause and look at this. 1 plus cosine of 2 omega t. That should ring a bell, because if we have cosine squared of x plus sine squared of x, we know that this is 1. And if we have cosine squared of x minus sine squared of x, this is the cosine of 2x. So adding these two together, we get that 2 times cosine squared of x is 1 plus cosine of 2x. And that is precisely what we have here, except that x is omega t. So we can rewrite this as 2 times cosine squared of omega t. And now we have omega t here and omega t here. And we can also factor out a 2. So we can divide by 2 because we have 1 here. So divided by 2, and this becomes a 2. And now notice what we have inside. So inside we have x squared, and then we have minus 2, I'm going to write it like this, minus 2x a cosine of omega t plus a squared cosine squared of omega t. So what I'm hinting at is that what we have inside is simply x minus a cosine of omega t squared. So let's write it down here. So this is minus m omega over h bar times x minus a cosine of omega t squared. And there we go. This is the probability density. And we can see that this is a Gaussian, right? We can look at this as y is equal to x minus a cosine of omega t. And this is a Gaussian, since this is, y is here going to be squared, right? This is e to the minus something y squared. This is a Gaussian. So it will be something like this, but it has this oscillating factor, cosine of omega t. So it's going to be oscillating with an amplitude a and a frequency of omega. So that is the probability density. And we just described the motion of the wave packet. Now we need to describe or compute the expectation values of x and p and check that the Ehrenfest theorem is satisfied. So the expectation value of x is the integral over all of space of x times the probability density squared, right? This thing squared. And we already can see where this is going, right? Because this, if we use this thing here, is integral from minus infinity to infinity of square root of m omega over pi h bar, and then e to the minus m omega h bar times y squared. And now instead of x, we can, from here, as we did in other problems, we can see that x is y plus a cosine of omega t. And dx is simply dy. So from this, we get here, instead of x, y plus a cosine of omega t, dy. So let's calculate this. So here we have two integrals. Now the first one is, let's see, minus infinity to infinity. We can pull out the constants to the front. So m omega pi h bar, and then we get y e to the minus m omega h bar y squared dy, and then we get plus, we can pull out a cosine of omega t to the front, minus infinity to infinity of, let's see, now we have square root of m omega pi h bar e to the minus m omega h bar y squared dy. So these are the two integrals that we now have to solve, but this is actually going to be much simpler than one might think. So this one right here is 0, because this is an odd function over a symmetric interval, right? We have this part is even, but this makes it odd. So for that reason, bam, 0, right? I'm always telling you, try to, whenever you're dealing with like a hard integral and your interval is symmetric, check if your function is even or odd. It might make things easier for you. Now here, we have something else. So we have a cosine of omega t times, now notice of course that this right here is psi squared. So here we are basically checking if our function is normalized. If it is normalized, then this is 1. If it isn't normalized, then we will get, the factor. So let's check if it is normalized. So we get the integral of minus infinity to infinity of e to the m omega over h bar y squared dy. But this is simply a Gaussian integral, as we have seen many times before. And the value of a Gaussian integral is simply square root of pi divided by this thing right here that goes along with the y squared. In this case, m omega, and the h bar goes up here. So we can see that pi, h bar, m omega. So our result is a cosine of omega t. So this is the expectation value of x. Now, what is the expectation value of momentum? So the expectation value of momentum, we know that it is m d expectation value of x dt. So in this case, this is m, and then we derive this, so we get a minus a omega sine of omega t. Right, so ma, yes. And now we want to check the Ehrenfest theorem, which tells us that minus the spatial derivative of the potential has to be equal to the time derivative of the expectation value of momentum. Now, since our potential is 1/2 m omega squared times x squared, so we have to take the derivative of x squared with respect to x, which is simply 2x. So here we can take out the constants and we get minus m omega squared times the expectation value of x has to be the same as the time derivative of the expectation value of p, which is this here. So we get minus ma omega squared cosine of omega t. And now let's plug in on the left side the expectation value of x, which is right here. So we get a cosine of omega t. So we have a cosine omega t minus m omega squared minus n omega squared. So the Ehrenfest theorem does hold. So there we go. We have finished problem 2.45. And as you can see, it was pretty straightforward. The calculations may have been a little bit tedious, but it wasn't really anything too crazy. So I hope that this was useful to you. If it was, please make sure to leave a like on the video, comment, and subscribe. It really helps me out a lot and it doesn't cost you anything. And if you really enjoy my content, maybe consider checking out my Patreon and sharing this video with some of your classmates. So I'll see you in the next video. Thank you very much for watching.